For our second example, for the pumping lemma, we consider a language that is a bit more complicated. And the language I would like to look at is the language a to the power of n, such that n is prime. So this is the language that consists only of a's, but the amount of a's needs to be a prime number. And I claim that this language is not regular. And I also claim that it's possible to prove using the pumping lemma that it's not regular. And well, we'll just start and see how it goes. So proof. Pumping lemma. As usual, we assume that L is regular. So assume L is regular. And if L is regular, then there is a constant P by the pumping lemma. Then there is P as a P taken from the natural numbers by the pumping lemma. Such that all the words in the language L, so then there's a P in the natural numbers by the pumping lemma, such that for every word that has a size of at least P, they can be subject to the pumping. So the first thing we have to do is we actually have to find our word Z. The word Z needs to be in the language L, and it has to have a size of at least P. So we just choose a prime number that's greater than P. And this prime number must exist because there are an infinite amount of prime numbers, so we can just take one. And we'll just say let n prime be prime and n prime should be greater or equal than P. For this n prime, then Z equals a to the power of n prime is for sure in L, because n prime is a prime number, so it's in L, and it has at least P characters. So by the pumping lemma, there's a possible decomposition of the word Z. Z equals UVW, such that the length of UV is less or equal than P. Of course, V only consists of A's. That's something we know because there are only A's in the word Z. So there can't be any other character. So we know that V has the form a to the power of k, let's say. As there are only A's in Z, V has the form V equals a to the power of k. That's something we know. Now we consider using the pumping lemma. And in the pumping lemma, the third part is the actual pumping part. So we consider U, v to the power of I, W. And this is the amount of A's in UVW is a to the power of n prime. If we add V once, we get k more A's in the word. If we add it twice, we get 2 times k, and so on. Adding one version of V means I equals 2. So the amount of A's in the word is actually n prime plus I minus 1 times k. Because if I equals 1, the word is u, v to the power of 1, which is v, w. So it's the original word z. If we insert one v, we increase I by 1, so we end up with I equals 2, and there are k more a's in the word. So pumping using using I actually yields the word n to the power of n prime plus I minus 1 times k. The goal is that this word here should not be prime. That is, the amount of a's should not be prime anymore. So it has to be a composite. And it would be nice if we could factor out n prime. And that's actually easily possible. We just have to make sure that this one here, this part, we can control the I, this we can control, and it would be nice if this part was actually n prime. So we would like to have n prime equals I minus 1. But that's easy. We just assume that I equals n prime plus 1. So we define I to be n prime plus 1. We can choose I, so it's perfectly fine to choose it whatever we like. So we define I to be n prime plus 1, and then this word v to the power of I, w, equals a to the power of n prime plus n prime plus 1 minus 1 times k, which is the same as a to the power of n prime plus n prime times k. And this can be written as a to the power of n prime times 1 plus k. And now we know that this is for sure no prime number. This is not prime. Because we found a decomposition as a product. There's a factorization here. It has two factors at least, n prime, which is prime, and 1 plus k, which cannot be 1 because k must be greater than 0. So 1 plus k is at least 2. So n prime times 1 plus k is for sure not prime. If the exponent is not prime, then the word is not in the language L. So therefore this is not in L. And that's the contradiction to the pumping lemma. So this is the contradiction to the pumping lemma. And L is therefore not regular. Not regular. And that concludes the proof.